Welcome to the GCE panel notes, Physics Advanced Level. In these high school physics lessons, we are going to be looking at dimensional analysis, vectors and scalars, moments and couples, equilibrium, right down to gravitational fields. Please subscribe to this channel if you are interested in having more videos and watch through these videos for free. Don't forget to subscribe and share all these videos to the different platforms in which you find yourself. In the first lesson, we are going to be looking at dimensional analysis. In this particular lesson, we will trash physical quantities, basic and derived quantities, dimensional analysis, homogeneity of equations, developing physical expressions, numerical examples, and exercises. Please watch this video to the end, and in the next, we are going to be looking at scalars and vectors. You can equally get materials from our channel, websites, and online courses. You can join our online course where we're going to be teaching you a lot of things in mathematics. This is just season 1, episode 1 or chapter 1 of the full package. You can follow this full course by registering on our site where you will be tutored from A to Z and be given the XYZs of mechanics and other branches of physics. So what is a physical quantity? A physical quantity is a quantity that can be observed and measured, and this includes force, velocity, temperature changes, density, and so on. So these physical quantities are the building blocks of physics in terms of which the laws of physics are expressed. Now, there is something you must note. Qualities like happiness, anger, hunger, love, ugliness, beauty, and so on are not physical quantities, since they can be observed but not measured. For example, you can see that somebody is really hungry or angry, but you can't measure the amount of anger or hunger. You can see that the lady is beautiful, but you cannot measure the quantity of beauty. Physical quantities are classified into basic or the fundamental physical quantities and the derived physical quantities. Such a division is arbitrary because a given quantity can be regarded as basic in a given set of operations and as derived in another. Let's start with the basic physical quantities. There are actually 7 basic physical quantities, which are mass, time, length, temperature, electric current, amount of substance, and luminous intensity, as shown in figure in table 1.1 below with their units and dimensions. Okay, please don't forget to subscribe to this channel for more videos. So in a tabular form, let us look at the different physical quantities that we have, the basic ones. So we have mass, time, length, temperature, electric current, amount of substance, and luminous intensity. These are the basic physical quantities. Now their symbols. The symbol for mass is small m, time small t, length small l, temperature capital T, electric current capital I, amount of substance small n, and luminous intensity LV, capital L small v. Now the unit for mass is kilogram, for time seconds, length meters, temperature is in Kelvin, not degree Fahrenheit or degree Celsius. Those are other units, but the SI unit of temperature is Kelvin. That is what you're going to be using in your calculations for Boyle's law, Charles and gas equations, and so on. Equally, for electric current, the SI unit is the ampere, amount of substance is the mole, and luminous intensity is measured in candelars. For the symbols of the units, mass is in kilograms, that's kg, seconds, small s, meters, small m, Kelvin, capital K, the electric current, capital A here, okay? Here is capital A, this is a slight mistake. Then for the amount of substance, which is the mole, it is MOL. Luminous intensity is capital C, small d. Note here at this position, we have A, okay, capital A, because current is in ampere. Lastly, for the dimensions, in working with physical quantities, you might be working with dimensions. So the dimensions for mass is capital M, time is capital T, length is capital L, temperature is T, electric current is capital I, amount of substance is N, luminous intensity probably C. Now, sometimes when we talk about time and temperature, the T's there might be somehow, so it might be adjusted when you're working with different physical quantities, okay? So take note about that. So some classifications, they might use K instead, though it might sound funny. So the magnitude of a physical quantity is expressed as a numerical value and the units, okay? Now for the derived physical quantities, there are many of them, they're uncountable. Unlike the basic ones that we have 7, the derived ones are uncountable. For example, we have length, we have area, volume, density, and so on. So many different quantities which are made up of multiples, multiples, powers, and so on of the other basic physical quantities. So the derived physical quantities expressed in 2 or more of the basic units, okay? So they are expressed in 2 or more of the basic quantities, e.g. velocity, acceleration, volume, density, impulse, flux, work done. In table 1.2, we look at some derived physical quantities, their symbols, their units, their abbreviations, and their base units. Now, the base units are the units of the basic physical quantities themselves. For example, we have velocity, the symbol is small v, the unit is meter per second, that's SI unit, okay? There are larger units like kilometers per hour and so on. And the abbreviation is ms to the power -1, that's meters per second. The base unit is equally meters per second. Acceleration is small a, the unit is the meter per second, abbreviated meter per second 2, or meter per second squared, and the base unit is the same. For force now, the unit of force is the Newton. But the Newton is not the basic unit of force, okay? So this is the unit of force, but it can be expressed in its basic unit as kilogram meters per squared second. Note that force is mass times acceleration, so we can see mass in kilogram, acceleration in meters per second squared. Energy or work done is in joules, capital J, and joules is like force times distance. So we just take force and multiply by distance. That's going to give us kilograms, meters squared per second squared. Then power P, the unit of power is the watts. And the watts is abbreviated capital W. The power is the work done per unit time. So we just have to divide the joule by time or by second. You're going to have kilogram meters squared per second cube. Pressure is measured in pascals. And the basic unit of pascals is the kilogram per meter per second squared. So you can download these notes from the link below this video or from our website so that you can have a better clue or understanding of it, or maybe you want to keep it for later use. This continues, the table continues on the next page. So equally we have electric charge in coulombs, the basic units there, ampere second, because charge is equal to current times time, ampere second. Potential difference V in volts, and this is the basic unit of the voltage, kilograms meters squared per second cube per ampere. Resistance is measured in ohm, and this is the basic unit of the ohm, okay? Capacitance C is measured in farads. This is the basic unit of the farad. Magnetic field strength is measured in teslas, and this is the basic unit of the Tesla. You'll see most of these concepts as we progress to current electricity and statics, electrostatics as well. A magnetic flux, the Weber, the symbol of the phi there is measured in Webers, where this is the basic unit of the Weber, kilogram meter squared per second squared per ampere. Electric field strength or electric field intensity is measured in terms of volts per meter, and that's the basic unit, as well as temperature gradient, which is measured in kelvins per meter. We are going to see this one in thermodynamics, in heat in general. All right, now let's move on to dimensional analysis. In dimensional analysis, we are going to be working with dimensions, okay? So dimensional analysis, also known as similitude, is a mathematical expression of physical quantities using their dimensions. So dimensional analysis, also known as similitude, is the mathematical expression of physical quantities using their dimensions. Also note that in an equation expressing the physical relation between physical quantities, absolute numerical and dimensional equality must exist. So in any equation, the dimensions on the left-hand side must be equal to the dimensions on the right-hand side. And equally, any numerical constants on the left-hand side should be equal to those on the right-hand side when simplified. Okay, so that's why we mean here that in an equation that expression between physical quantities, absolute numerical and dimensional equality must exist. For instance, the equation below, the dimensions on the left-hand side and those on the right-hand side must agree or be equal. In addition, the constants must also be equal on both sides. So this is further explanation of what I just mentioned before. So here we have this equation KL square M cube is equal to alpha L to the power 4 M to the power minus 3, all that on L square M to the power negative 6. So if we simplify the left-hand side, or the right-hand side rather, because the left-hand side is already simplified, the right-hand side you will have L to the power 4 and L to the power 2, which is L to the power 2. So it matches the L on the left-hand side. And then M to the power negative 3 divided by M to the power negative 6, M to the power plus 3, which agrees with what you have on the left-hand side. Okay? And you can equally start at this point now, K must be equal to alpha for this equation to be consistent. Okay? So there is absolute numerical and dimensional equality in this particular case. Okay? So there is consistency. Let's now move on to homogeneity of physical equations. A physical equation is homogeneous if it satisfies the following three conditions. So for a physical equation to be homogeneous, it must satisfy some three basic rules. The first, the exponent, the unit, and the dimensions of each quantity on both sides of the equation must be the same. So a physical equation is homogeneous if the exponent, the unit, and the dimensions of both of the quantities on both sides of the equation are the same. But note that homogeneity is not a true test for correctness. Why? Because an equation can be dimensionally homogeneous, but physically incorrect or wrong. So this is why homogeneity is not a true test for correctness. Because you can see an equation which is dimensionally homogeneous, but it is physically incorrect. Let's look at an example of this equation, which is dimensionally homogeneous, but physically incorrect. So the equation force is equal to amount of substance times mass times acceleration, where F, or this it can be refractive index, F is equal to force, N equals refractive index, N equals mass, A equals acceleration. This is dimensionally homogeneous, but physically, this equation is incorrect. Thus, we must always check homogeneity and correctness. Let's take some examples. Here we take some past standard exams. Example 1, the period of a simple harmonic oscillation of a floating bobbin is T equals 2 pi root M on density gravity area. Show that the equation is homogeneous. So this is the equation of a simple harmonic oscillation of a floating bobbin that relates the period to its mass, density, gravity, and surface area. So we want to show that this equation is homogeneous. So M here is the mass, T is the period, G is gravity, A is area, and this is density. This was a 2010 paper 2 question 1 item taken from 2010 paper 2 question number 1. So let's tackle this. So the density, the unit of density is kilogram per meter cube. This density, mass is kilogram, area is meter square, and gravity is meter per squared second. Now let's work with the left-hand side and right-hand side. So for the left-hand side, for T, that's period, the unit is S. Now for the right-hand side, we have root M, because these are constants. 2 pi is a constant, so we don't talk about the units of 2 pi. So root M on rho GA will have units. M is kilogram, rho is kilogram per meter cube. Gravity is meter per squared second, and area is meter squared. When we simplify this one, we are going to have everything will cancel out. You'll be left with the square root of S squared, which is equal to S. And what do we observe here? This is equal to the left-hand side. Sorry, not the right-hand side. This is equal to the left-hand side. So at this point, therefore, with respect to units, this is our conclusion. Therefore, with respect to units, the equation is homogeneous since units and exponents on the left-hand side and right-hand side are equal. So this is how we answer the question in an exam. Okay, so with respect to the units, it is homogeneous, dimensionally homogeneous. Now, example 2 reads, the pressure at a point in a fluid is related to its density and depth at a point according to the relations given below as P plus rho A plus B rho H equals C. Explain how units can be used to test for correctness of the physical equation. Determine the units of A, B, and C. So how can we use units to test for the correctness of a physical equation? So for this, the units must be homogeneous. That is, units on the left-hand side must be equal to the units on the right-hand side. This is how we use units to test for the homogeneity of physical equations. Okay? So when you simplify the units on the left-hand side and simplify those on the right-hand side, they should be equal. That's how we can use units, like you just saw in the previous example. B, what are the units of A, B, and C? I'll start with C. The units of C are the same as the units of P, which is the Pascal. Okay, because we are summing pressure plus pressure plus pressure is equal to pressure. Okay, so the units of C is the same as the units of P. So C is in pascals. But I would like to give my answer in terms of the basic units. The Pascal is given like kilograms per meter square per second square. Now the next units, the units of A. So the units of A are the same as the units of pressure divided by density. So I'll just say A, the units of A should be equal to pressure. This is the unit of pressure divided by the units of density. And that gives me m squared per second squared. This is the same like velocity squared, okay? Now the last one, the units of B. The units of B are same as the units of pressure on density times depth. So I have this, my units of basic units of pressure, the units of density times depth, okay, which is meters. So the units of B is meter per squared second. So B is acceleration. So this is how we answer this question. You can download these questions from our site, or you can request for these questions. We are actually preparing students the GC in our panel and other exams. So you can contact us if you need a tutor online, and we make an arrangement, or you join other students who are studying for 2024 exams and so on. All right, let's move to example 3. So in example 3, the surface area A of the skin of a human body is given roughly by the expression 8 to the power 4 equals km squared h cubed. This is June 1988, paper 2, question 1, where m is the mass in kilograms, h is the height in meters, and k is a constant. Determine the dimensions of k. B, if k is 1.6 times 10 to the power negative 3 units, estimate the body surface area. So in this question, we have given an estimate, so that we have the same answers. Let's say the average height is 1.7 meters and the body mass, average body mass is 72 kg. Let's just use this. Though this was not in the exam, but to make us to have the same values, but this is an estimate. So here, solution. The dimensions of A is L square, of H is L, of M is M. So want to find the units of K, we just make K the subject of the formula and simplify. So K will be equal to A to the power 4 on M squared H cubed. But the units of A are L squared, so L squared to the power 4, all that on M squared. Units of H are L, so L to the power 3. When you simplify, you start the dimensions. So if you give the dimensions of K, not the units of K, the dimensions. So the dimensions of K are L to the power 5, M to the power negative 2. Okay? This L to the power 2 times 4 is L to the power 8. L to the power 8 divided by L to the power 3 is L to the power 5. And here we just have 1 over M to the power 2. Now B, if K is equal to 1.6 times 10 to the power minus 3 units, estimate the body surface area. So from here, we already know that A is equal to this. So to make A the subject of the formula, A will be equal to the 4th root of Km squared H cubed. So this is equal to the 4th root, or all of that to the power 1 over 4. So we have 1.6 times 10 to the power negative 3 times 72 squared times 1.7 cubed. When we simplify this, that the surface area of the human body is roughly 2.5 squared meters. Roughly 2.5 squared meters. Question or example 4, these are the numerical examples we are talking about in this particular tutorial. Example 4, Newton's universal law of gravitation is stated as F equals G m1 m2 r squared. Describe the different symbols in the equation. What are the units of the physical quantity G? Explain why an equation 1, which is not homogeneous with respect to the unit, may be wrong, and 2, homogeneous with respect to units may not less be wrong. Okay, so this question was June 2002, paper 2, question 4, extracted from that paper. So let's see. Describe the different symbols in this equation. When you do Kepler's laws of gravitation and so on, gravitation, you'll see all of these Newton's universal law of gravitation as well. So from here, this G is a universal gravitational constant. Okay, F is the force of attraction between M1 and M2. That's the mass M1 and the mass M2. R is the distance of separation, or the distance separating M1 and M2. M1 is the mass of object 1, M2 is the mass of object 2. So those are different symbols in the equation. Now, what are the units of the physical quantity G? So for the units of G, we just have to make G the subject of the formula and simplify it as we saw previously. So we are going to have G equals F R squared on M1, M2. So for F, you have kilograms meters per squared second. R squared is M squared, and F is kilograms times kilogram. So when you simplify, you're going to have M cubed, S to the power minus 2, and kilograms to the power negative 1. Those are the units of G. Now C, explain why an equation 1 is not, which is not homogeneous with respect to units, may be wrong, and 2, homogeneous with respect to units may not less be wrong. So the first one, if an equation is not homogeneous with respect to units, it must be wrong because the units on the left-hand side are different from those on the right-hand side. Okay? So for an equation to be homogeneous, the units on both sides of the equation should be consistent. So this is a matter of inconsistency. Now the sub 2 of C, if the equation is homogeneous with respect to units, it may not less be wrong, okay? So with respect to that, it may be wrong because homogeneity, as we previously saw, is not a true test for correctness, okay? So it may still be wrong because homogeneity is not a true test for correctness. All right, now we move on to example 4. Okay, that was example 4. Now note that in this our series for mechanics, we have season 1, which is mechanics. And in this particular series, physics mechanics A level, we have dimensional analysis, chapter 1, chapter 2 is vectors and scalars, chapter 3 moments and couples, chapter 4 equilibrium of forces, chapter 5 frictional forces, chapter 6 kinematics 1, chapter 7 kinematics 2, chapter 8 motion under free fall, chapter 9 projectile motion, chapter 10 Newton's laws, chapter 11 force and momentum, chapter 12 work, energy and power, chapter 13 connected particles, chapter 14 circular motion, chapter 15 simple harmonic motion, chapter 16 Hooke's law, chapter 17 rotational dynamics or rotational motion, and chapter 18 gravitational field. All these lessons are very short lessons. We advise you to watch all these lessons, subscribe and share to promote this work we are doing if you really enjoyed it. Here under connected particles, we'll be looking at pulleys as well as inclined planes. We now move to the next part of the course, which is developing expressions, developing physical expressions. So in the previous section, we have seen how to test for homogeneity, which we will now extend to developing physical equations and expressions, given various parameters and assumptions. So example 5, develop a physical expression for the distance s, assuming it is a function of weight w, acceleration a, and time t. That is, s is equal to a function of weight, acceleration, and time. Okay, so here we are going to develop a physical expression that relates distance with weight, acceleration, and time. So we start by looking for the dimensions of time. It is t. Dimension of acceleration is L on t squared. Dimension for distance is L. Dimension for weight is ml on t squared. Okay? So now S can be written as a constant, because this is a function, right? A constant times the weight to the power A times the acceleration to the power B times time to the power C. We are now going to solve for these constants A, B, and C, working with the dimensions on both sides, equating dimensions, okay? So here, dimension of S is L, then we have K, which is a constant. W is ml on t squared to the power A, these are the dimensions. And then for A, it is L on t squared to the power B. Then for time, we have just t to the power c. So at this point, we can now simplify the right-hand side and equate dimensions on both sides of the equation. We have k, m to the power a, l to the power a, and t to the power negative 2a for this first one. Then for this for the second, we have l to the power b times t to the power negative 2b. For the last, we just have t to the power c. Bringing like terms together, we are going to have L to be equal to K times M to the power A, there's just single M, L to the power A plus B, this L again, then times T to the power negative 2A minus 2B plus this C now, okay? Minus 2A minus 2B plus C, laws of indices. At this point, equating dimensions as well as powers, we see that for A or for M, there's no M on the left-hand side, so A is equal to 0. Okay, then for L, we have A plus B to be equal to L to the power 1, so A plus B equals 1. And since A is equal to 0, it means that B is equal to 1. Lastly, negative 2A minus 2B plus C is equal to 0. Knowing that A is 0, B is 1, C should be equal to 2B, which is equal to 2 times 1, which is 2. Therefore, S here will be equal to K times W to the power 0 times A to the power B, beta B is 1, times t to the power c, but c is 2. At this point, w to the power 0 indicates that w is not a function of distance, so it's not part of it. So thus, s is equal to k a t squared, where k is a constant that can be determined from experiment or maybe experimentally, as they usually say it. So this is a physical expression we have developed for this particular equation. I don't know which year was this, but it was taken from one of the years. So here, this equation is homogeneous and physically correct. We know that s equal to half at squared, right? So k is a constant that can be determined from experiments. Okay, so the last thing is that since you have w to the power 0, it shows that w is not a function of the distance of this object that may be falling freely or whatever. Guys, please make sure that you leave your likes as you watch this video. Don't forget to subscribe and to share this video. If you really want to promote our work and to appreciate what we are doing, why not? You can contact us directly and leave your tips or whatever. You can equally subscribe and share so that when many people come to know about this, we are equally being promoted. We thank you so much because we know that we are benevolence. We know that with your happiness or your appreciation of what we are doing, you will share this video not just on WhatsApp groups, on Facebook and other media. You equally put this video on your blogs so that people can watch them as well. Thank you so much in advance. Let's look at the second example under developing physical expressions, example 6. So in example 6, a body falls freely for a distance s from rest. Develop an expression for the velocity. Whenever they say from rest, it means gravity is included. I'm giving an example, I will not indicate that. You need to know that from rest means include gravity. So from here, we can say the velocity of the particle is a function of its distance and gravity. So the dimension of velocity is L on t, and since they say it's falling freely, it's under gravity, so the dimension of gravity is L on t squared. At this point, we can say V is equal to K times S to the power A times G to the power B, where we are going to solve for A and B. So here, L on T is equal to a constant times L to the power A times L on T squared to the power B. Simplifying gives us, on the left-hand side, LT to the negative 1 equals, on the right-hand side, K times L to the power A times L to the power B times T to the power negative 2Bs. Bringing like terms together, we obtain LT to the negative 1 equals K, L to the power A plus B, T to the power negative 2Bs. Equating dimensions and their powers on both sides of the equation, we always take the one that is always alone or easy to solve. We have negative, for T is negative 2B equal to negative 1. From here, B equals half. And for the L's, the powers of L or dimension L, A plus B equals 1 implies that A is a half. So A is a half, B is a half. This can therefore be written as V is equal to a constant times S to the power a half times G to the power a half. Okay. So if we can square both sides, we will have V squared is equal to a constant. This constant K here now replaced with the capital K. It's a different constant now. Going square constant becomes another thing, okay? A constant SG, KSG. Okay, or this could just be written as V is equal to A root SG. Anyway you write it is still okay. So take notes. So here, which is homogeneous and physically correct, and K is a constant that can be obtained from experiments. Okay, you know V squared is equal to 2ax from experiments, right? So from here, K should be equal to 2 from experiments or from standard equations in physics. You know V squared is equal to 2as. All right, so this brings us to example number 7. This brings us to example 7. And example 7 reads, a body falls freely from rest for a time t. Develop an equation for velocity. So the dimensions for t is time, velocity is L on t, gravity is L on t squared because they said freely. So just like the previous one, so we have V equals K, G to the power A, T to the power B. Let's call this equation 1. Next, dimensions for V is L on t is equal to K times L on t squared to the power A times T to the power B for time. Simplifying both sides, we'll have LT to the negative 1 equals K into L to the power A, T to the power A times T to the power B. Bringing like terms together, we obtain LT to the negative 1 is equal to K, L to the power A, T to the power negative 2A plus B at this point. So from here, you can see that A is equal to 1, A equals 1, and negative 2A plus B is equal to negative 1. But knowing that A is already equal to 1, from here B will be equal to 1. At this point, our V will be equal to K, G to the power 1, T to the power 1. And this finally gives us V is equal to K, G, T. Well, K is a constant that can be obtained from experiments. And this equation is also homogeneous and dimensionally correct. In physics, we know that V is equal to U plus 80. But the object is falling, our U will be equal to 0. So since it's falling from rest, we just have V is equal to U plus 80, right? Yeah. So example 8, as we said, there are many examples in our work. In the next, we will be looking at vectors and scalars. After this, graphics and scalars. Guys, please don't forget to subscribe and to share the video. Example 8. Develop an expression for the frequency of a simple pendulum, assuming it's a function of the length L, mass M, gravitational acceleration G. So just like the previous questions, the dimension of frequency is 1 over T, is T is the power negative 1. Acceleration is LT to the negative 2, mass M. So frequency is a function of K, L to the power A, M to the power B, and G to the power C, the parameters we have mentioned here. So at this point, frequency T to the negative 1 should be equal to A, L to the power A, M to the power B, and our G is LT to the power negative 2, L to the power negative 2, all that to the power C. All that to the power C. So therefore, we will now have negative 1 is equal to K, L to the power A, M to the power B, L to the power C, and T to the power negative 2C. Equating dimensions, or further simplifying, we have T to the power negative 1 equals K, L to the power A plus C, M to the power B, and T to C. All right, now let's equate the dimensions and see what we have. Equating dimensions, it will be because there's no B on the left-hand side or there's no M on the left-hand side, B equals 0. Then for T, negative 2C is equals negative 1, so C equals a half. Lastly, A plus C is equal to 0. Okay, so A plus C equals 0, implying that A, okay, this is supposed to be C here, implying that A is equal to negative a half, since C is a half. So therefore, we have this expression as Kf is equal to K, L to the negative a half, G to the a half. Since B is the M is not included. Finally, F is equal to K root L on G. So we can finally simplify and have that. Okay, you already know the constants there. You already know what the constant there is. Okay. So this example 8 and all these 8 examples give us the numerical or the multiple examples we are talking about. Okay. So this equation is genus and dimensionally. One other thing that we would like to talk about is that we are having preparatory classes online for those who are writing 2024 and beyond. So registrations are going on and the classes are very cheap per course. So you can join our online courses where we prepare for the GCE and other exams. So contact us, get to us, because we don't want people coming late to disturb us. Contact us so that you can join to take an online course. And from our lessons, you can know if you can carry out. Okay. In the next video, we'll be looking at vectors and scalars. Now let's look at some exercises that you have. So our multiple examples here are, you have example 1 to 8. So you can go through all those examples again from example 1 to example 8. Vectors and scalars. And these are exercises, miscellaneous exercises. Develop an expression for the period of a simple pendulum, assuming it's a function of the length, mass, and additional acceleration. So this one will give you T equals 2 pi root L on G, unlike the other one that we just had. This one now is $1 billion one. Please solve this one, and you can send a video. You can send the solution of this one to us. Let us discuss it, or you can type it on the site, website where this video is. Let's discuss, or the YouTube below this video. Tell us how or what you have here. So the intensity of an electromagnetic wave in a vacuum is related to its peak value E0 of the electric field, with the wave by the equation L equals half epsilon 0 E squared C, where E0 is a permittivity in vacuum. Okay. Okay. Show that the units of the equation are consistent. So thank you so much for watching. And this is the outline shows dimensional analysis, vectors and scalars, moments and composite equilibrium of forces, work power, energies, force and momentum, connected particles, projectile motions, Newton's laws. All of you are doing pure math mechanics. This one is also very, very important for you, okay, from vectors and scalars and so on, because you can see all of this in math, pure math with mechanics. So take note. Thank you so much. Please subscribe to our channel. Share this video on YouTube. Share on Facebook, share on WhatsApp, on TikTok, share on different platforms. Please encourage guys to get to these videos and also get to our platform so that we can actually build a bigger community of knowledge sharing. God bless you as you prepare for your exams, and ciao. GCL.